More than 1,000 NIMS visitors have observed this fiber-fuse demonstration since 2009. We receive a number of frequently asked questions from them. How high is the temperature of the bright spot? Why didn't I feel the heat inside this optical fiber in my hands if it is at such a high temperature? In this video, we will answer these questions. It is quite difficult to measure the temperature of a moving object like a fiber fuse running along an optical fiber. If the target is motionless, we can estimate its temperature through the color of its emission. In 2006, a group of Russian researchers conducted the following experiment. They inserted a Y-shaped optical circuit in a fiber fuse experiment system and initiated a fiber fuse in a fiber made of silica glass. Then, they measured the visible light emission spectrum from the bright spot approaching to the detector through one port of the Y-shaped circuit. As a result, the temperature was estimated to be on the order of several thousand degrees Celsius when initiated with a several watt laser beam. Why we are not burnt when a heat source of several thousand degrees Celsius travels over our palms? We will be able to find a reason if we pay attention to the volume of captured plasma in the fiber. The optical fiber we use in our demonstration is categorized as single-mode fiber for optical communication. Inside the thick protective layer, there is a glass fiber of 0.125 millimeters in diameter, in which light propagates in the central region of 0.01 millimeters in diameter, called core. On the other hand, the diameter of sheathed cable is 0.9 millimeters. In other words, if the central heat source were to continue to heat the surrounding solid layer nearly 8,000 times larger in volume for a sufficient period of time, the surface of the fiber cable would get hot. However, the bright spot is running at a speed of about 1 meter per second and stays on the palm within 0.1 seconds, which is too short to heat the cable surface. This is how we are able to observe the light emission from the object of several thousand degrees Celsius from up close. You cannot observe this phenomenon using any optical fibers other than silica glass fibers, because of the unique properties of silica glass. Thanks to its extremely high softening temperature, the fiber is tough enough for the passage of a tiny high-temperature object through it. There have been no reports of similar fiber fuse phenomena in other glass fibers. However, in 2014, a similar-looking phenomenon was discovered in a polymer optical fiber. There is one thing different from the former case: a very slow propagation speed, about 2 centimeters per second, pumped with a smaller laser power of about 0.1 watts. This means that a completely different phenomenon occurred in this case. That is, a part of fiber core absorbs laser light, carbonizes the core with heat and light emission, and moves toward the laser light source. Consequently, the running bright spot along the optical fiber appears only if a delicate balance is established between the fiber material, propagating light energy, and the light-induced reaction. Finally, we will point out a well-known phenomenon that has something in common with fiber fuse propagation. A grass fire is a linear formation of fire over a field full of dried grass that propagates to burn it. It also has a reaction region emitting heat and light that moves toward the energy source. Grass fires also exist on the edge of energy flow in a combustion reaction. The scientific name for such a phenomenon is a dissipative soliton. Any dissipative solitons extinguish when the energy flow balance is lost. A grass fire goes out when the dried grass supply is exhausted, or if it is caught in a heavy rain. A fiber fuse disappears when the laser light is shut down, or the captured gas is released to open atmosphere due to some defects on the fiber surface. Based on this idea, various devices for terminating fiber fuse propagation have been proposed up to now. Please read this book if you would like to learn more.